Our next speaker will be Alexsander Immer. Alex is a PhD student in machine learning at the ETH in Zurich, where he works on probabilistic machine learning and data science. And Alex was a master's student at EPFL, and during his time at EPFL, we collaborated together to create an algorithm called Predicon that we use for making predictions of elections and referendum. So Alex, whenever you're ready, the floor is yours.
Hello, thank you for the kind introduction. Yes, I'm Alexsander Immer, and I'm gonna talk about the project I did at EPFL together with Victor, Matthias Großklauser, and Patrick Tirant. And it's about submatrix factorization for interpretable real-time vote prediction. And the focus here should be on interpretable and real-time. So we try to do that on the day of the vote. And this was basically sort of a paper last year, but it also is, as Victor said already, a project that is still live, and it is available on predicon.ch, and you can find online predictions for each referendum in Switzerland. So I'm sure many of you followed the presidential election last year, and it was kind of a very, very long race. And it took a lot of time until Biden could be confirmed as a winner. And one of the reasons for that is actually that there's a bias in how these results are released. So for example, you have different time zones in the US, and also different states have different sizes and different number of votes to count. So it takes different times until you can get the results. And then it's very hard to extrapolate to make a national prediction as well. But it is very important to be able to predict for news outlets, political parties, interest groups, as well as citizens. And therefore, we sort of try to have a very general algorithm that allows us to make predictions on the vote day without having to simply extrapolate. And the overall goal that we have is to predict aggregate, so national vote outcomes from partial results that are, for example, regional on different regional levels, and those that arrive sequentially. So in a very realistic scenario, that would be what happens on a vote day. And there are two key assumptions that sort of help us design this algorithm and also are very realistic at the same time. So for example, the first one is basically that results are released sequentially, and this is almost always the case. And very often you have also access to these sequential results. Of course, this is something that came up more and more due to open data initiatives that you now have access to such sequential results online as well. And the second is that regions have biases and are correlated. And this is very, very obvious if you, for example, compare cities as well as countryside regions, and those have very, very different, let's say, very different voting patterns over time. And we assume that these are correlated across time as well as generally. And if you now apply a very simple extrapolation like averaging, you will usually fail, and you will basically have a very biased prediction. And our algorithm that we designed basically exploits these sequential results to correct the bias. And what exactly we use to do that is we look into the historical correlation between votes. So you can imagine that we have a bunch of these voting patterns over the last 20 to 50 years, and we look into how these regions behave across time. So do they change a lot, and when do they change their sort of when do they change the outcome? And another thing is that we incorporate the correlation of regions, and this is very intuitive. So, for example, let's take this small county here or I don't know if it's small, but let's take this county here in South Dakota, which has a Democratic majority in this case, and there might be another county which is far away, but it's in Alabama, and it's correlated. Historically, they always both vote for the same party. And there might be another county in New Mexico which is anti-correlated historically. So once we know the outcome of one of these three regions, we might be able to predict the outcome of the other regions due to their historical correlation. So they sort of move in an ideological space always in the same way. And then exploiting this kind of data that we historically have about vote outcomes, we try to make real-time vote predictions. So this is really much really similar to what many of us followed in the end of last year. So we observe sequentially one region after the other, and hopefully we converge and make the right prediction. But not in every case. We have just red and blue, especially in Switzerland, which is, I think, a very interesting case to study for such political data. We have referenda. So in these referenda, it is not really clear what is red or blue, because each question might lead to the positive answer being either more right-leaning or more left-leaning. For example, here, we have a referendum about agriculture and environment. And then if you vote in favor, one could say this is rather left-leaning. And you can see that the west of Switzerland is rather in favor of this, which is the French-speaking part, and the east of Switzerland is rather against it. But then there might be another referendum about deportation of criminal foreigners, where the patterns are completely different. And here, voting in favor is rather right-leaning, and voting against is rather left-leaning. And you can see the pattern is entirely different as well. The green regions, which rather vote in favor, are now more countryside regions, and the ones that vote against it are rather cities. So Zurich, Lausanne, Geneva are rather red. And our algorithm doesn't really care about this kind of strict political ordering of, let's say, two parties, or in this case, in the American case, red and blue. But rather, we just assume some kind of observed votes of the past. And we'll basically automatically find this ideological landscape of regions. To do that, we have basically only given this vote matrix, which is collected over time. So votes are historical votes, and regions are the regions of interest. And these can be on different granularities. So it can be counties, districts, or even states. And so each region has its kind of row of historical data, and each column would then be a vote where you have outcomes, for example, for a single referendum. And once we observe one of these entries, this would tell you the fraction in the case of a referendum, the fraction of yes voted for in this region. And it might also be that you have multiple values there if you have, let's say, 5 options for different parties. And now what happens on vote day in terms of this vote matrix, it can be modeled as a new vote, as a new column in this matrix. But these are only partially observed, because we don't observe them following our assumption all at once, but we sequentially observe them while they are counted. And then we have some which are grayed out here, and those are unobserved. And we don't know the values of those, but we would like to know it so that we can make a national aggregate prediction ultimately. And the first step of our algorithm is to obtain regional embeddings by doing a singular value decomposition. So submatrix factorization basically corresponds to doing the singular value decomposition on the fully observed matrix of regions and votes. And this allows us to find these regional embeddings. So kind of, well, later, as we'll later see, will be the ideological landscape of regions and vote embeddings. And this will allow us then to reconstruct one entry of the matrix by the corresponding regional embedding multiplied with the corresponding vote embedding. However, once we look at one of these outcomes that we couldn't observe yet, we don't really have the corresponding vote embedding yet. So what we apply here next is simply a linear model. So we take the values that we have observed, and we take the corresponding regional embeddings, and then we learn the new vote embedding simply by this linear model. And this is a generalized linear model in this case, so we can even model different likelihoods. So we don't really have to see it as a regression problem. We can also see it as a classification problem for multiple parties, for example. And then once we want to fill out these missing entries, we simply use this model and have to compute this product as well. And this will basically make the this vote matrix fully observed. And then we can extrapolate and make predictions about the whole vote, because we can simply, we basically simulated the observation of all these regions that we didn't know the results of. So why is this interpretable? First of all, we have a GLM, so a generalized linear model, which is very easy to interpret, but it is only interpretable or easily interpretable if the features are also clear, right? So to show you why we believe that the features are very interpretable, let's look into some examples. The first one here is the regional embeddings of the German ideological landscape of votes from 1990, after 1990, so after reunification. And as you can see here, due to the coloring of each region by the majority party, there is kind of a split axis through it. And on the right, you have the CDU, CSU rather on the right hand side, and on the left, you have the SPD, which is rather a bit left-leaning. And interestingly, this is also regional, to be confirmed, that in the southern part, you rather have CDU and CSU predominantly, and in the northwestern part, the SPD. And this already shows there might be some other pattern here, because there are two very, very distinct clusters. And of course, these correspond to the historical East and the historical West gap. And interestingly, Berlin here is kind of very close to the border and it's a bit undecided, which also kind of makes sense. Our Predicon system, however, works on Swiss referenda. So that's the real-time setting we deploy it in. So let's also have a look at the Swiss political landscape. And also here we find very interesting patterns in our regional embeddings. And these are predominantly scattered by color. So here you can see on the left a German cluster of all the German regions, and on the other side of the line you see the French-speaking municipalities. And what's in between is basically this ideological border, also called Röstigraben sometimes. And the Italian cluster is kind of noisy and lies on the German side, but it's kind of a bit undecided as well. And these are basically these orientations across the language, but also you have, again, regional patterns here within these clusters. On the top right, we can identify the bigger cities like Basel and Geneva and Lausanne. And the bottom, you find rather smaller regions that some of you might not have heard of. And based on these embeddings, we designed an online system that since last February predicts referenda online. And since then, we have predicted 9 referenda with quite good results and with a very low error after observing the first outcomes of regional results. So here we look at the performance of our algorithm right after observing the first batch of results. So that's at 12 p.m. of the day of the vote, and we have only 13% of the results available. And at that time already the prediction is just 1 percentage point off, or around 1 percentage point. And also, if you look into the prediction over time, it looks really rather impressive. You have our model in red, SubSVD with a Bernoulli likelihood. And you can see the prediction does not change so much over time, but eventually converges to the true value. And our baseline here, which is a simple averaging, really kind of fails because of all these biases. Especially in the bottom, you can see that it changes very rapidly, so it fluctuates a lot and is therefore quite noisy. And the reason for that is that the outcomes of particular regions that give us a lot of vote and a lot of information is observed at these times, and this creates all the noise. And averaging, of course, cannot alleviate the bias as our algorithm can do. However, we also found, while our system was live, we found another issue, and that is that there are some referenda where the outcome is very, very close to 50%. And then users cannot be so sure about if they should trust this prediction or if it might change and sort of cross the 50% boundary. And so let's look into one of those examples. So in this case, we have the referendum from last year about responsible businesses. And as you can see, our algorithm in red, again, after 20 minutes makes a right prediction and also remains at this prediction. And opposed to this, averaging, again, doesn't work so well. And it takes 3 hours more until you get the right answer with that algorithm. However, because you're very close to 50%, and still fluctuations might affect also our algorithm, it might happen in some cases that you get very close to 50% and the user might wonder, how sure can your algorithm actually be? Is it well calibrated? And we sometimes probably cannot perfectly rely on this algorithm, or we would at least like to know how sure can we be about this prediction. And as Victor mentioned, my current research is about probabilistic machine learning, and I'm very interested in Bayesian machine learning in particular. And what I applied here is Empirical Bayes. So I optimize our SubSVD or a generalized linear model for uncertainty. And this will basically give us a Bayesian SubSVD algorithm that solely has on top of the original prediction some kind of credible interval here. And here I plot shaded in blue the 99% credible interval. And this is a very big, although it's a very small change, it allows you to give very different predictions suddenly. So now the prediction is not binary between yes and no, but rather it is accompanied by a confidence score. So here you have in the beginning at 12 p.m. something like a 50-50 chance. That's at least what the algorithm says. But then over time, let's say 1 hour later, you're already at around 65% confidence that the vote outcome will be yes. And this is sort of, for the user, it is a bit better to sort of know when you can be very, very sure, which would be here, let's say around 3 p.m., because then all the credible interval is actually above 50%. And if you look into the comparison against averaging, you can see that at that time the averaging algorithm was still wrong. I would very much like to invite you to look at our website, predicon.ch. The political life in Switzerland is quite high frequency, so every around 3 months you can see our predictions for the votes live on Sunday, and the next one will be on 7th of March, I believe. And we also have visualizations of regions as well as the geological landscape that I showed before. If you're interested in looking at the data, the code and the Python library are online on GitHub, and details on the method can be found in our paper, Submatrix Factorization for Real-Time Vote Prediction. And if you're interested in hearing more about the Bayesian approach, of course, feel free to contact me. I'm happy to talk about that as well. Thank you very much for your attention.
Thank you, Alex, for the very clear presentation. We don't have questions from the audience yet. Again, please don't be shy and ask some questions in the chat. I have a question for you regarding the Bayesian prediction that you have with the uncertainty. We see that at the very beginning, of course, we don't have a lot of data, so there is a lot of uncertainty. What could you do in order to reduce this uncertainty at the very beginning? Okay, yeah, to reduce the uncertainty, I think there are different ways we can go. So one way would be to incorporate additional data. This would, of course, give you more signal, more information. So, for example, take poll data into account, as we heard in the previous talk. This could be interesting to make the model more confident at the beginning with few observed results. And another way might be to find a more suitable model. So maybe the generalized linear model doesn't allow us to perfectly fit this data, and we need something more complex here. It might be possible that maybe a neural network with one hidden layer will sort of allow you to fit that data a bit better, a bit faster, and reduce uncertainty. Okay, Thank you very much. And we have now a question from the audience, from David Brown, who's asking, so you talked about predicting final voting outcomes based on partial data, and do you think that there is other use cases for this algorithm?
Yes, I think so. I definitely think so. It is very much rooted as well in terms of recommendation systems due to this matrix factorization algorithm, and sort of the related work is very much also from the recommendation systems community. So if you have the sequential problem where, let's say, you observe about users in the past and you know about sort of their interests, but you only need to fill in sort of a few new interests in an online way, then I think this algorithm can be applied in this very specific scenario as well, and would work better than traditional recommendation system algorithms. But yeah, I think probably in many settings where you have these complete matrices, and then you have one time axis where you observe sequentially. But I cannot think of any particular other application right now.
Okay, thank you. And there's another question by Stephen, who's asking how well does your algorithm fare on the cantonal level?
Okay, so on the cantonal level, I'm not aware right now of the numbers of the results exactly, but it's much harder because you have less cantons, so you observe only one at a time, and it will be much more noisy. So we had, for example, we did the same on the German data, and there we can do it on a state level. And if we do that in German data, then observing one result can change your prediction more than observing, let's say, 20 municipalities at the same time. But it still works better than averaging, because you still have very strong bias. And this you also can see, for example, in the US, where you also do it on state level.
Okay, thank you. And we just received 2 more questions, so I will quickly ask you these questions, and then we'll take a coffee break. So the first question by Sylvain Robert is about, have you tried adding informative features besides your embeddings, such as the language of the region, city, countryside, and so on?
Actually, yeah. So within this project, in the Indie Lab, it was done before that they added other information about on the cantonal as well as the regional level, and that also can help. But interestingly, we found that with this particular algorithm, it didn't improve the performance so much anymore, because you can actually, as you can see in our regional embeddings, identify a lot of these features from the ideological landscape already. However, I think it would generally help you to improve the predictions a bit more as well. The reason why in this case we didn't do it is that we wanted to have a general purpose algorithm. So in many cases, or in many countries, you don't have that data available. You just basically have this historical data available, and it's very hard to get additional data on the regions. And so this algorithm can be applied to all settings right away. And I think if you want to add in more information, it's very easy, because you can use this generalized linear model framework. So basically you add to that regional feature vector and fit your generalized linear model with this additional data.
Thank you. Other question by Oleg Lavrovsky. Your results are compelling, but I wonder if the explainability of the process, the ability to trade through specific outcomes, is something that could be improved to foster trust. Or what else would you say is important to actually include these results in the political process?
Yeah, I agree. It's of course it's not perfectly reliable, interpretable at all times. I think this is also why we tried this Bayesian approach now, because it allows you to quantify all these uncertainties a bit more. So be very defensive about your statements. So as opposed to saying this will be definitely a yes in the referendum, you say it will be yes with 60%, and the region, sort of the ideological landscape, is approximately like this. So I think it's very important to be kind of defensive and careful, and not make very strong statements.
Okay, and we have one last quick question by Ahmed Jelouli. He was asking, when you're factorizing the matrix, do we use only the first 2 singular dimensions? And if we use more than 2, are those results still interpretable?
Okay. For the results, for the prediction, for the online prediction, We use more. We use usually up to 10 dimensions. And you can also look into these different dimensions. At least you can basically do the same scatter plot for different dimensions. The first 2 dimensions are particularly interpretable because they're usually regional along one axis and sort of the language in Switzerland across the other axis. But the other dimensions that you will find out also usually have a very interesting interpretation to them. And if you look at the website on predicon.ch, you can have a look at a TS&E plot as well, and that will kind of show more than the first 2 dimensions. So there you will see that actually regions like municipalities even cluster by canton. So the singular dimensions after the second, those will tell you a bit more about the cantonal kind of clusters that you would get. So I think it's still interpretable, but of course you should look into these dimensions as well.
Thank you, Alex, for all these answers, and thank you for all the questions from the public.
Yeah, thank you.
Congrats again. And so we will now take a 10 minutes coffee break. We highly encourage you to connect to the networking tool so that we can now have offline discussions online. So see you again in 10 minutes.